Okay, so we just did empirical formula. Now we're going to go through balancing chemical equations. So far, all the problems we've done in this class so far, we didn't have any actual chemistry going on. When I say chemistry, I mean reactions. Okay, we didn't have any reactions happening yet. We have to talk about balancing chemical equations first, and then we can do problems that involve having chemical reactions. So balancing chemical equations really involves one law that you must know. It's the conservation of mass, and then also conservation of charge when it comes to redox chemistry in particular. But mainly it's the conservation of mass. Conservation of mass means what? Well, that's the first. What is that? Well, yeah, that mass is neither created nor destroyed in any process. So yeah, that's a technical definition. But in terms of practice, how would you say it? Okay, whatever mass I start with has to equal the mass of the products I get out. So that's another way of saying it. But yeah, you're right. Mass is neither created nor destroyed. Whenever I hear that, it confuses me with the first law of thermodynamics, which is energy is not created nor destroyed. So I kind of got confused there for a second. Anyway, so mass has to be conserved. Okay. So here's the guideline that I say you should follow for balancing chemical equations. It's different from how I've seen it in any textbook. It's just how I verbalize it. So the first thing you want to do is write a basic equation, one of each reactant and product. Most textbooks will also say this. But here's the way I do it differently. And that is just that I say balance atoms mentioned only once on each side first. So if you see an element mentioned twice on one side of the arrow or the other, leave that for last. Okay, or if there's multiple atoms like that, leave them for last. If you try to balance those atoms first, it gets much more difficult. Okay, and then balance the atoms that occur as free elements. Usually those are the ones that were mentioned twice on one side or the other. And then if the balance equation contains coefficient fractions, you would need to multiply the entire equation by a denominator to get rid of the fractions. Yeah, any question?
Can you remind me what free elements are?
Free elements, like diatomic elements, oxygen gas, like O2 by itself, chlorine gas, I2, Br2, they have no free bicycle beverages elements. Those are like free elements. White phosphorus, rhombic sulfur. Okay, and then by the time you get rid of all the fractions, then lastly you want to check the equation, make sure that the same number of atoms are on both sides of the arrow. So everybody knows the basic structure of the equation, right? You've got reactants on the left, products on the right, you've got an arrow, you've got plus signs in between each reactant and product. Does it matter what order I write the reactants and products in? Like, does it matter? Like, would I say methane plus oxygen goes to CO2 and water? Or could I say oxygen plus methane goes to water and CO2? Like, does it matter how I write the order? And the answer is no, all right? A chemical reaction or chemical equation is just that. It's a chemical equation, all right? It's the same thing as saying x plus y is equal to y plus x. Okay, there's that mathematical, statement there. So they call them chemical equations because they really are mathematical statements of the chemistry. If you look at old papers, old publications in chemistry journals, sometimes you'll see equal signs instead of an arrow. Right, kind of interesting, huh? Okay, so let's do an example. Write a balanced equation for the combustion of gaseous butane, C4H10. Okay, so the hard part is I'm giving you English and you have to convert it to chemistry. So what is well, it gives us butane. All right, so we know we can say butane is C4H10 and it's plus what? Plus oxygen. How do I know it's plus oxygen? It says the word combustion. So anytime you hear combustion, that should probably ring a bell to you to say, okay, we're burning something in oxygen, and the product will be CO2 and water if we are burning a hydrocarbon, which most of the time is the case. time it wouldn't be a hydrocarbon. Sometimes they burn metals, and you could say that's combustion of a metal. But usually when we say combustion, we're talking about burning fuel, burning hydrocarbons. Okay, so what are my products? H2O and CO2. By habit, I always just say CO2 and H2O, but you can write it backwards, it's okay. So first step is always write one of each reactant product on both sides of the arrow. It says gaseous butane, so we'll go ahead and do that. Oxygen is always a gas, unless otherwise stated. Carbon dioxide, what's the phase on that? That's also a gas. And water could be a liquid, but typically when you're burning a hydrocarbon, you're producing water vapor, right? So we got gas there. So what's next? What do we balance first? Well, let's look at what elements are mentioned twice on one side or the other, and then avoid that. So carbon, is that mentioned only once on the reactant side? Yes. Is carbon mentioned only once on the product side? Yes. So we can start with carbon if we want, but let's just assess the other elements. Hydrogen mentioned only once on the reactant side. Hydrogen mentioned only once on the product side. So we could start with that too if we wanted. Oxygen mentioned only once on the reactant side, but it's mentioned in two different products on the product side. So because it's mentioned twice on one side of the arrow, we say, let's save oxygen for last. So you see the analysis there? It's just, let's look at the elements that are balanced, or that are mentioned in only one compound on both sides of the arrow. We'll start with those. So for carbon, since it's the first one listed there, I'll just start with carbon. So how do we balance carbon? We got 4 here. We need to put a 4 in front of there. And then what about, let's see, next is hydrogen.
5.
We got 10 here, so we need to put a 5 in front of the water. So remember, the coefficient applies to everything in front of it, of that particular reactant or product. Okay, so now here comes the slightly trickier part. We have our carbon, we have our hydrogen, those are balanced. Last thing is the oxygen. So we've got to count our oxygens on both sides to see what we have. So from the CO2 with the 4 in front of it now, how many oxygens do we have there?
8.
We have 8. 8 O's. And then we have for the water, how many O's do we have from that?
5.
We have 5 from that. So adding those together, we have a total of 13 O's on that side. On this side, we only have 2 O's. So the question becomes 2 times what number, we'll call it x, is equal to 13 on the other side. It's some non-integer number, right? So it's going to do 6.5. Or you can say 13 halves. Okay, so now, go ahead and rewrite this. C4H10 plus O2 4 CO2, 5 waters. And so now we're going to have 13 halves, or 6.5 for the oxygen. If you left it like this, it would be balanced. Okay, that's actually balanced. But we know that it doesn't make sense for half an atom or half a molecule to react. It's just not normal. So what can we do? Multiply through the whole equation by 2. right? So one thing that you usually see with combustion reactions, the number that you get on the product side ends up being the final coefficient for the O2 on the reactant, just because it's always going to be something half, 13 halves. Okay, so we end up with final balance reaction, C4H10 plus 13 oxygens, 8 carbon dioxide, and how many waters? 10. Now in your master in chemistry homework, they might be particular about the phases, so just be in the habit of including your phases. All right, any questions about balancing chemical equations? All right, it gets more exciting, okay, but that's just the strategy that I use for balancing. All right. I've got it up here too. So all combustion reactions happen like this. Sometimes you don't have to multiply through by an integer because it just happens to come out as an integer. Right? All right. If there's no questions, we'll